Welcome back to my channel. In this session we will see a transformer-less power supply. In common words, voltage dropper circuit. When we discuss any power supply, it must have a step-down transformer, step-down circuit. We apply 220 volt and it will provide some closer value to our requirement. Then we apply to a rectifier circuit. Then we store on capacitor, and then we provide these DC voltage to any load which is our requirement. In last session we discussed how we can calculate resistor to power on this LED to apply with 220 volts. But here we will not use transformer. This circuit is unisolated power supply. The first thing, unisolated. We cannot use it in any open circuit. It must be in any concealed device, concealed box we can use it. If we want to test with multimeter, if we want to test with oscilloscope, we must take care that this is unisolated circuit. The second thing, this circuit provides low current. First of all, we will see what we need. We need output voltage 5 volt. We want to turn on this LED. Our basic requirement to turn on this LED. Why I added this resistor? This resistor is normally used to control the current. We can design directly a 1.8 volt voltage dropper, but that will not safe. For that purpose we need a capacitor, we need a zener, so that it will protect this LED and it will compensate the voltage variation, because this circuit will directly take power from the line voltage. For that purpose we need some voltage here, and we will connect a capacitor across this LED, and we need a clamper regulator, voltage regulator, that is zener. It is a protection, and we will provide bridge rectifier here. To drop the voltage we need some voltage dropper circuit. For that purpose we will use these capacitors. Why we will use these components? We will see. First of all, I will give a simple example of the circuit, and we need to add a bleeder resistor. This is dropper capacitor. It is normal polyester capacitor, ceramic capacitor. We can use X-rated capacitor. We can use class X capacitor, and we need a surge protection resistor. How we can determine the exact values of these components? If you have 5.1 volt zener, 5 volt zener, that is good. This time I have 6.2 volt zener. What is available? I will design at this 6.2 volt, and we need 20 milliampere maximum to drive this LED. I out 0.02 ampere. This is our requirement. Now what is the input voltage? In my area it is 235 volt to, I will consider 230 volt, 50 hertz, and our load, that is 5 mm LED, that have V forward 1.8 volt. Its maximum current is around 30 to 35 milliampere, but we will consider it 20 or 15 milliampere. Let's start. We know that these are DC components. Active components, unidirectional components, LED, zener, these are DC components. To deal with DC components we need bridge rectifier. For that purpose we will consider these DC voltage. Total input voltage 230 volts. AC RMS 50 Hz. Now we need to convert these voltage into peak voltage because these are RMS voltage. So V peak 230 square root 2, or we can multiply directly with 1.414. It is 325 volt. We provide here 325 volt. We need 6.2 volt at this rail. That means we need any circuit that can drop the remaining voltage. Now from this point to this point we have 6.2 volt, and if we see in both lines, in the positive rail and the negative rail, all the time we have two diodes in series. This diode and this diode. This diode or this diode. So both diodes, the drop voltage for one diode, that is 0.7 volt. V out, that is 6.2 volt, and here we will drop 1.4 volt because two diodes will remain forward bias. So our total load, we can see, if we see from this angle, from this point forward, so we have two loads, the one diodes, the second load. 6.2 plus 1.4, 8.68. From this point forward it is 8.68 volt DC. So the remaining voltage 325 minus 8.68, that is V drop, minus 325, it is 316.32. 316 volt DC. So if we analyze this circuit from this point to this point, we need 316 plus 1.4 plus 6.2 volt. It will equal to 325 volts. So we want to add some resistance here, or anything that will equal to this resistance. Let's calculate the resistance. We know our load current is 0.02, 20 milliampere. So 20 milliampere will flow in the circuit. If we calculate the resistance value, R is equal to V over I. Voltage 316 volt divided with 0.02. 316 divided with 0.02, so it is 15800 ohms. This is our resistor value. When we say resistance, that means it is the obstruction in the current flow. Resistance, that is passive component. It works in DC and AC. But here we are using AC circuit. In AC circuit, if we want to add some resistance, that can be XL, that can be XC, that can be inductive reactance, that can be capacitive reactance. We can use any of two items. Now we will use the capacitor. We know the XC, capacitive reactance, is 1 over 2 pi FC. In this formula we want to use it in full sine wave, 360 degree. Frequency is 50 Hz. We want to know the capacitor. Capacitive reactance, we know that we know this resistance. Capacitor will be 1 over 2 pi F XC. 1 over 2 pi, 3.14, 50 Hz, and XC is 15,800 ohms. 15,800 ohms. So it is 2.01. 2.01 10 raised to power 7. If we shift one digit to the left side, so it is 0.201 10 raised to power minus 6. So now it is in microfarad, or we can convert it in the nanofarad. That will become 200 10 raised to power minus 9, or 200 nanofarad. Convert it into pico, 200 1 2 3. This is picofarad. So if we see the capacitor code, it will become 2 0 and 1 2 3 4, 204 PF code. The second thing, we want to know the value, because we are using in DC voltage around 316 volt. It can charge up to 316 volt. So next higher value we can select 400 volts. If we check the capacitor code, capacitor chart, after 184, the capacitor code 184, there is 224. We want to use 204 code. For that purpose, I will use 104 plus 104. 100 nano plus 100 nano, it will become 1 plus 1 2, 0, 4 will common, so it will become the same. If I will use 224, that will become large value, but I will use these two capacitors in parallel to make our required value. Capacitor, first of all, discharge the capacitor before connecting to multimeter. It is for safety. It is 99.6, that is 100 nano. It is 198.6, so we can say it is 200 nanofarad. When we will use this 200 nanofarad capacitor, it will provide 15,800 ohms resistance in the circuit. When we will use this capacitor, at that time we need to add a bleeder resistor here across this capacitor. Why? Because when this capacitor is charged, it is an AC circuit. It have no isolation. Even if we remove the power supply, this capacitor will remain charged. It can give electrical shock. For that purpose, we need to connect a 1 mega ohm resistor across this capacitor to discharge it. It is called bleeder resistor or discharge resistor, because it is also passive load. We don't want to add a current consuming or power losses, because its duty is just to discharge the capacitor. And also this is in a concealed environment, so we need a slow discharge. If we will add fast discharge, at that time we will add a permanent power dissipation with this circuit, because it will also in parallel to the circuit. So we need a high value resistor with low power watt. So we will use this resistor. We can say R1. R1 value is 1 mega ohm, 0.25 watt. The next component, we need these diodes. Our required current is 0.02 ampere, so that is a very low amount of current. So we can use 1N4007, a simple rectifier for line voltage rectification. Then we need BZX 85C6V2. It is 6.2 volt, 1 watt regulator. That's good. We can use also 0.3 watt, 300 milliwatt. That will good, but it will useful. Why? Because we have to protect this circuit from surge current, and it have a good repetitive peak current. So we can say it will helpful when we will rectify these voltage. This positive end, this is negative end, and this will regulate the voltage, and these rectifiers will work as a series resistor for this zener diode because it have also series resistance. So we no need to add a series resistor for regulation purpose. In case of any over voltage, it will protect the circuit. 47 microfarad capacitor, 50 volt, or we can use 25 volt. It is 6.2 volt. We can use 16 volt, 25 volt. 47 microfarad capacitor, 25 volt or 50 volt. I have this time 50 volt. I will use 50 volt. You can use 16 volt, that is good. 25 volt, that is good. 35 volt, that is good. Now we need to calculate the value of this resistor, that is V supply minus V LED divided by I LED. 6.2 volt minus 1.8 volt, and we will just calculate with 0.015 ampere, that is 15 milliampere. 6.2 minus 1.8 divided 0.015, it is around 293. We will use the next higher value, that is 330 ohm resistor. It is 330 ohm, and if we will use 6.2 minus 1.8 divided with 0.02, that time 220 ohm. If we will use 220 ohm resistor, that time it will give more brightness, but we will consider 15 milliampere, that is very good. Now we need to add surge protection resistor. When we connect a capacitor here, at initial stage it behaves like a short circuit. Why? Because when it is empty, its resistance is equal to 0 at that time. When the capacitor is connected, it will charge 63%, then 63%, but at this point it will draw maximum current. For example, our system current is 0.02 ampere, but for initial charging, this is time in microsecond in this capacitor because it is low value capacitor. Around 10% of the value, it will provide a short circuit, then it will reach to a normal current. So we need to limit this current in this portion. Even if we don't use anything, our both components, this LED and this zener, these will protect. If we don't use, it can damage this LED, but we need to add some resistor here. If we see LED, light emitting diode, it can take up to 1 ampere peak forward current for 1 microsecond. Okay, so that means if we don't add any component at that time, it can charge this capacitor. If we connect just one LED, it can handle up to 1 ampere surge, that is peak current. Here we are using resistor, that is 330 ohm. We are also using a resistor here. In the same time, we are using these diodes. So that means there are many protection devices to limit the surge current, because these diodes are also protecting the current, and this capacitor value is very low. Moreover, in our this BZX85 series zener 6V2, it can take up to 6 ampere IZSM, that is peak non-repetitive peak current, that is one pulse, up to 6 ampere. So we can say if we don't use any component here, it will work normally. We will add 56 ohm resistor, 1 watt, that is excellent. If we add a high resistance, we can say 1 kilo ohm, at that time it will also become a load. We can also determine this charging time by this formula. C is equal to the total current, delta time, delta voltage. Now I completed the circuit. We can also make this circuit on PCB. We can also make this circuit on Vero board, but this time I am not making on project board, just to demonstrate and give a clear concept that our current will enter from here and it will be rectified through this bridge rectifier. These cathodes are coming to the positive terminal of this capacitor. Anodes of both diodes, this diode and this diode, is coming to the negative side. So this is negative side here. This is positive side. We have 330 ohm resistor and 6.2 volts regulator. Yes, now it's good. Take care that it is an isolated circuit. We must remember this point, that this is an isolated circuit. Now I will connect to 230 volts. Now I install this circuit here so that every connection is visible now practically. Now I will power it on. Yes, it is now powered on. Let's see its voltage. Never touch any component because it have live voltage. AC voltage at input terminal, that is 231 volt, as we discussed here. Frequency 50 Hz, 230 volt. This resistor is just dropping 800 millivolts. That's good. If we select here some high value resistor that will dissipate more power, at that time it will become a permanent power loss. Basically this circuit is very low current consuming component, but if we add unnecessary resistor here to protect these capacitors, these are low value capacitors, 200 nanofarad, and we have 1 ampere peak current here and 6 ampere current here. So that means we can just only add NTC. That's will useful. And if we see the voltage drop across this capacitor, it is 228 volts. So here is 228 multiply with 1.414, 322. We calculated that we want to drop voltage 316. That's good, because here we are consuming 15 milliampere. If we will use 20 milliampere at that time, it will draw more current and here voltage drop will decrease. And this time if we check voltage in the output of this dropper, at this point we have 7 volts in the output of this capacitor and this resistor. That's nice. So 7 volt RMS multiply with 1.414, that is 9.87. So we said 8.68, that is good, because we calculated the capacitor value at 201, but we are using 200 nanofarad, and it is not 200 nanofarad, it is around 197 nanofarad, I think. So that is the reason it have slightly more voltage here. That's okay. Let's check the DC voltage. It is 6 volt. Excellent, because we are using 6.2 volt zener. This time, as I discussed, that these diodes will behave as a zener series resistor. If we check voltage drop across this diode, this time it is dropping 2.9 volt, 3 volt. Normally the diode drop voltage are 0.7 volt. So it will drop the voltage and our required voltage will reach here, 6 volt. Out of 6 volts, this LED will drop 2 volts. We allowed it 1.8 volt, and this one 3.9 volts, the resistor, the series resistor. Okay, another point, if we calculate practically this capacitor value, it will around 1 microfarad. I am using 47 microfarad. If we will use 1 microfarad, 10 microfarad, that will good. that will also work nicely. And if you use higher value like 47 microfarad, it will reduce the ripples. If you use 10 microfarad, 25 volt, 35 volt, that is excellent. And if we reduce this resistor around 22 ohms, that will also useful, but 56 ohm, that is excellent. I hope so you enjoyed this video. If it is good, hit the like button. If you have any question, let me know in the comment box. Thanks for watching. Assalamu alaikum wa rahmatullahi wa barakatuh.